Okay, so we're going to start with a simple linear regression. And here will be a little bit mathematical than the previous when we're doing the review. And why we are covering it again, the syllabus said we should cover it is one of the statistics background. So we start with an example of a simple linear regression. Now, as we know earlier, simple linear regression means our independent variable or the predictor is only one. So for example, we have two dimension x. Let's say x is my independent variable, x to determine y, so y become my dependent variable. Now when we talk about multiple regression, then in this case we have more than one independent variable. Now in this section, the syllabus, I think there's no need to cover, or let's say if we have time, we're going to cover multiple regression also. So example they gave here, we have a serial data, then the serial is right here, different brands, and each contain information of 77 serial brand, including sugar and rating example. Now our goal, suppose we want to estimate the rating of cereal only if sugar is given. Again, we can't do multiple regression, so multiple regression where independent variable can be more than one, but here we are doing simple regression. So what we mean here is that is sugar the predator to estimate the rating. So here we are going to use the sugar for that. If it's possible, if sugar can do it, let's see if sugar can do it. So normally when we're going to do regression is about prediction. I'm trying to see if sugar can predict the rate to go up or down. So normally what we do is that we have to start with scatter plot. Even in statistics, they tell us that. So we start with the scatter plot. We'll get something like what we have here, the visualization of the data. And we can see in this data set, we have a decreasing pattern. Majority of the data close to the line is going down. Beginning it was up, then going down slowly. So that would be when sugar increase, rating goes down. Or when sugar decrease, we can also see that rating. So again, forget to mention, sugar is the horizontal rate, always the independent variable, the predictor always will be horizontal. The response variable or the target, the dependent variable will always be vertical. So based on this data, the data set we want to work on, we were able to visualize it here. And then we can see a pattern of, as we said earlier, decreasing. So this will tell us that as the sugar increase, the rate goes down. When the sugar decrease, again, the rate will go up. We can use this, but another option also is to find the correlation value. So we can determine the correlation, and that true value can tell us if there's a relationship between the rating and sugar. Now, if there's no relationship between rating and sugar, then there's no way we can do prediction. We cannot say if there's no any association or relationship between sugar and rating, then we cannot in the future say that if sugar increase, rating will go down because there's no relationship there. So that's why it's good to do the correlation scatter plot, and if possible, use the value also to find it. So our goal here, we have the blue line. This blue line is the best fit line, the line that have most of the points on it or very close to it. So we will call the line regression line, or estimated regression equation will be this. So y caret here always is about prediction. So y will be the actual value of y. We may have the y mean, we may have y caret here. So y caret here gives us BO plus B1X. Again, BO will be the y-intercept. Y-intercept means when x equal to 0, what's the value of y? And as we said, our main goal is to get as much points very close to the line as possible. Because if it's close to the line, then our total estimated error, or if they use the term residual, will be lesser. So the goal is to have less residue or less error. Okay, so if no question, let's keep going. Oh, okay, sorry. So B1 represents the slope. Now, B slope normally tells us the steepness of the line. Yeah. So our parameters here will be only x and y carat. That's what we're going to again. Oh, sorry, I say x. B1. X and y carat will be our, I would say, S is a coefficient or something, but that's where our data is. So S is our independent. Y carat is the dependent variable predicted. But what I want to mention before is BO and B1 will be like the equation parameters. Yeah, not BO. Okay, so let's keep going. So we already know what is I carat, as we said, is an estimated value of response variable. BO is y-intercept. Y-intercept means when S equal to 0, what's the value of y? Then we have the slope, which normally determine the speed and steepness of the line. So this is what we're trying to say before. Together with BO and B1, we have the regression coefficient. Now, the data set is not here, but when we apply the data set, this is the equation we generate. Actually, we can even use like Excel itself to do this if we have our data set. So the slope there, 2.42 times sugar, if we interpreted the ERA, is estimated serial rating equal to what? 59.4 minus what? 2.442 times the sugar content in grams. So again, 2.42 times sugar. So the estimated serial rate equals to, again, 59.4 minus 2.42 times the sugar content in grams. Wait for a few seconds if it's okay. So again, our slope is 2.42. Our y-intercept is 59.4. Okay. So that's the example again. This time we say x is 1. So since we were able to come up with this model, now we don't care. The sugar, which is x, can be any value we can be able to predict. So here, again, we are using 1 as x. We generate 56.98 for y carat. And this is where we are concerned about. The ERA prediction 2i by 56.98 minus 50.765. So the actual value of y in that so this is the vertical line here. So if all the points is on the line, that means there's no error. But we will draw a vertical line from each point to the line, and that will give us the error. And that's what we have here. So we have 56.98 minus 50.765. That gave us 6.215. And we say that value, y minus y carat. Again, y carat is the prediction y. is always prediction error or residual. And now this will be the regression equation, represent the true linear relationship between rate and sugar for all series. So we add the E, which is sum for error, to the equation. Now here they say suppose two or more series have same rating but different sugar content. Then here we're going to have error term E account for indeterminacy in model. Residual will give us yi minus y carat. Okay, so these are some few items we should go through. The least square estimate. Here we say suppose we have n observation from model, then we're going to have yi equal to bo plus b1 xi. And then let's keep going till I reach n. Then we also have the least square line that minimizes the population sum of squares. So SSE stands for sum of square valuation. Then we have population sum of square errors re-expressed. So we know difference will be yi minus y carat. Y carat is bo minus b1 s1. So we find a difference of that with the y value also. Then we have the least square estimate. Wait for a few seconds. If no question, let's keep going. So next we have the summation distributed, then equation re-expressed again. So here we have the BO n plus B1, the sum I from 1 to n xi. So this will give me S1 plus S2 all the way to plus Sn. And finally, we solve for BO and B1. Normally, to solve for BO and B1, first thing we need is, okay, we can use this formula, but there's some formulas also available to use, but again, we use this formula. So first thing we need, again, we can find the mean media. Here, this type of formula, we don't need a standard deviation. Standard deviation is this score, but there's some formula that we can use to replace this where you need some start values. Okay. So here we say the formulas produce BO and B1. Then least squares error, least squares estimate for BO and B1 respectively. So y-intercept is again the location where, again, the YRE intercept y is. So when s equal to 0, what's the value of y? And here also we say the YRE estimate a cereal with 0 grams of water to have again to have the 59 again 0.4 rating points. I think it should be in the next slide. Let's see. No. So again, we don't have the data, but let's say we have BO equal to y pound or y mean minus B1 x mean. So based on the data set, we can find both values, x mean and y mean. We plug in, we know B1, then we get 59.4. This is the B, the Y average minus 2.42 X average. So if we know the BO, we can find the B1. Use the formula here, we get negative 2.42. Okay. If we know the value of B1 and B1, we can come up with the equation. They didn't write the equation here. But again, the equation will be Y equal to, we know the BO, so Y will equal to 59.4. And the slope is negative, so it will be 59.4 minus 2.42x. Let's say x is our independent variable. So here we can do this concept manually. So that's the two formulas. To find the y-intercept, we use the formula. Then we have the slope formula also. Yeah. Then also we can work with the least square estimate also. Good news, a y-intercept is location where you are intercept y. But we say the value for response when when the predator equals 0. So here the ERE estimate a cereal with 0 grams of sugar. It will give us this. Because from the formula, okay, we don't have it here. We don't have the formula. Okay. Let's say this is the formula. If sugar is 0, then y carat will be 59.4. That's all we want to say. So value for response when predator equals 0. Here the ERE estimate a cereal with 0 grams of sugar. Again, will give us the y-intercept value, which is 59.4. That's what they said. Consider predicting a person's weight based on his height. But if you say the height is 0, that is unclear. And even a newborn baby, if you have some weight, you must have some height. Unless your weight is 0, then your height most likely will be 0 also. So in this case, y-intercept cannot be interpreted. For a few seconds, if it's okay. So here we know the B1, which is the slope value, negative 2.42. We can use it also. Sometimes also we use the coefficient of determination. Normally here we say that will give us coefficient of determination value also will be from 0 to 1, which is R square. So if you know the R value, you square it. That will give us the percentage that the input, the predator, spraying the Y, determine the Y. Let's see, I think we have it. No, we don't have it. So this is an example. We have this is the data set. We have 10 subjects. We have the S and Y values. So if I have the S and Y values, I can be able to find the Y carat, which is the predator score. We saw how it is. So we have to, again, work our way to find BO. BO, we use the mean of X and Y inside the BO. Then we have to find the slope, which we saw the special formula to use. So after we know the slope, what I'm trying to say is this, let's make sure we are on the same page. So this is the formula we are using. I find the BO, I find the B1, then I can write down the equation. So it will be BO if it's 59.4 minus 2.42x equal to Y. And that's what we are doing here. So we were able to find Y carat equal to 6 plus 2x. And we can see the error in prediction, then error in prediction square, which we call the sum square error. This is what we're going to use. So sum of square error will be the difference of the actual value of y minus the predicted value of y. So wait for a few seconds if not. Let me go there. So this is our scatter plot again. And the vertical line will give us the difference of y carat and y. So here we just finding the values. So for example, here we consider we cannot tell which is computer 10. But let's assume we have computer 10 where ignoring S value lead to this. So to give it the difference of the actual and predicted value. Also, we have the sum of square total, which will give us the difference of y. This time it's not carat, but the mean. So the difference of actual y and the mean all square. Then we are adding it. So I from 1 to n, let's say if it's only 3, then we find the difference of y1, y average plus y2 minus y average, but all square, then you sum all. So all square is very important. It's like finding the standard deviation. Total deviation always will give you 0 if you don't sum them. I mean, if you don't square. Squaring means we're going to ignore the negative answer. Because when the answer is negative, you square become positive. And that's the formula we have here again. SST equal to the sum from I1 to N, the difference of Y and the mean. So again, we don't have the data, so all these values, maybe we can use it as explanation. But as we said earlier, coefficient of determination, let's see if they find it somewhere, and they're going to use it to interpret the result. But that will give us percentage of the independent that determine the dependent. So we also have the SSR, sum of square regression. And by this time is y, difference of y carat and y bar. And normally SST, sum square total, is always equal to SSR plus SSE. So if no question, I think we're almost done with it. Also, we can find the R square using SSR over SST. As we said, R value always will be between 0. Because it's square, we're not going to get, for example, we know R value is always from -1 to +1. But R square, if R is -2, square will be positive. No, let's say if R square is -0.2, then square will be positive 0.04 and 2 decimal places, etc. So R square always will be a positive. Yeah, so here they gave us the meaning where R square is proportion of variability in response variable explained by ERE, by the independent data. Perfect. If SSE is 0, then R of course will be 1 and R square will be 1 also. So minimum value of R score occur when ERA show no improvement if it's high. We also have the mean square error, SSE over divided by n minus m minus 1. M again is the number of predators you have, and n is the size of the sample or the number of observation. We're almost there. Okay. It's kind of the slice is too long. Okay, so here also we have standard error of the estimate, and the concept is given here. Again, we don't have the value, the data, just the example of solving the problem. The R square value is very good, 0.9474, almost 95%. And also, as we say, correlation coefficient R, this value always will be between -1 to +1. If it's close to 0 or 0, that means there's no relationship between X and Y. If it's very big, positive value close to 1, then we have increasing relationship. When S increase, Y also increase. And the decreasing relationship means when 1 decrease, 1, if S decrease, Y will increase. And this is the approximate value for positively correlated if it's greater than 0.7. Between 0.33 to 0.7 is mildly positive correlated. Then close to 0 or 0.33 positive negative, there's no relationship, no correlated. And it's another way of computing the R again. And the example data we don't have this step. Okay, so we'll wait for a few seconds if any question. Okay, so we're going to stop the recording. No, we shouldn't end it. Maybe the next class. We just stay here. Stop.